20 minutes.
Yeah, you can start. It's fine.
So I thought of just going through the basics today. Like we'll cover why we use linear algebra and some basics of linear algebra, like rewinding to first year maths that we had and what's a qubit, basic stuff like that. It won't take too long, so I should be done by 6. We'll start off like we'll cover the basic history of like how we came up to this point of having quantum computers and even being able to use real quantum computers, and we have access to. The first thing is that in the early 1920s, like the reason quantum mechanics even came up to be was the issues that we had that we weren't able to explain in a, a ultraviolet catastrophe, reason why an electron doesn't just fall into the nucleus. Those were like unexplained, problems in physics, and quantum mechanics gave away by, quantizing energy to answer those questions. And people like Max Planck, Niels Bohr, Heisenberg, Schrodinger, all of them were obviously killed. And you know, then Einstein came up with, he was not very comfortable with the idea of quantum and the whole EPR paradox, and the way it was solved was else inequal. I'm just going very quickly through all of that and read it up if you. But the idea that you can actually use quantum mechanics to build a computer, because it feels a little far-fetched, was through Feynman. He had earlier done work on quantum electrodynamics, and in like around 1985, I believe, he thought, well, I want to simulate quantum systems, and well, classically, simulating quantum systems is quite hard. It's very computation heavy. So he decided, well, the best way to simulate a quantum system is using a quantum computer, and that is how the idea of a quantum computer was originally born. And Deutsch actually then extended that idea and came up with a quantum Turing machine and introduced qubits and quantum gates, and that was how field even started. Then eventually we got the Deutsch algorithm, Deutsch Jose algorithm, that showcase quantum parallelism, which is one of the ideas that, how exactly are quantum computers faster, or that they can indeed be more efficient than classical computers. And then, of course, we have the big breakthrough of Shor in 1994. He solved the factorization and discrete log problem much faster, exponentially faster than classical algorithms. But theoretically, of course, he hadn't like there was not a physical quantum computer then. And then we come to Grover's search algorithm in 1996, and he gave a quadratic speed up to a search algorithm that, like if you see a linear search of unsorted data, it takes, the worst case time would be O of n, right? So Grover's algorithm allows you to do it of root n. So that these two, like, I mean, of course, there are other algorithms. This is just the, basic outline. But these actually drove like a lot of interest into quantum computation, and Shor is still there. He is working on error correction. So it's pretty interesting. Now we'll move on to, linear algebra, which is the like mathematical model behind quantum computing and mechanics, honestly. And one of the reasons we have to understand is that, when we observe in something in the real world, right? If you say that you want to measure a velocity of car or something, you realize that it's not going to be at 10 kilometers per hour at one time, and the next second it's not going to go to 100 kilometers per hour. That does not happen. It's a continuous, increase that you see. Like even if it's a very fast increase, it's continuous. And at a given point in time, you only find one velocity of the car. You don't have the car is at two velocities at the same time. So a classical particle would, behave in a certain way, and based on that behavior that we observe in the real world, we like come up with a mathematical model that fits its behavior. Okay, I know that a classical particle is single valued and continuous. Therefore, what is the best mathematical thing that can explain this? Single valued and continuous sounds like something we've worked with quite a bit, functions. Single valued and continuous function can very aptly describe the movement or the velocity of a classical particle. Similarly, when it comes to quantum particles, the thing with them is they don't have continuous energies or continuous values. They come in discrete values. I mean, if you remember the hydrogen atom thing that we did in 12th or something, you know that the electron can only take up discrete energy values, right? So a quantum particle has discrete energy values, and the it can have any value randomly, but each value is accompanied by a certain probability. So each value has a certain probability of being measured. So that that sounds like so if you want to come up with a mathematical model to describe that, it would be like, okay, you have a coefficient that describes the probability, and then you have the value that actually holds the like the value of the energy or whatever it is that you're measuring. That sounds, I mean, again, it sounds a little abstract when I say it like this, but if you see it acts like a1 b1 plus a2 b2 and so on, and that, I mean, it it shows up as a linear combination. And again, I won't go into it too much, but the discrete values can be held in matrices as well. So seeing the behavior of quantum particles, physicists over many years, well, they decided the best way to describe and go about quantum mechanics and quantum computing would be to use linear algebra. That is the reason we use linear algebra, to because it very nicely describes the behavior of qubits and stuff like that. Now let's come to what is a vector space. So because we know that like qubits are represented in a special vector space. So what is a vector space? It is a collection of vectors that can be scaled by either multiplying, or you can add the vectors. So say you have certain basis vectors, by either scaling them or adding them, you should be able to cover all the points in that given space, and that's what a vector space is. So again, like by that definition, I don't know if you guys remember what basis vectors are, but basis vectors are the like vectors that are required to span, like they're linearly independent, and they span the vector space. Now, like a simple example would be our classical, this we've used like almost everywhere. A vector is equal to xi plus yj, where I hat and j hat are the basis vectors for that space. So in that two-dimensional plane, you know that by assigning proper values for x and y, you can like reach almost any point in the xy plane, right? So I hat and j hat are the basis vectors for that space. Similarly, so the number of basis vectors that you require to span a vector space is known as the dimension of the vector space, right? So now let's come to in which space exactly are qubits and quantum systems described. Like we work with Hilbert spaces, right? A Hilbert space is a vector, like a vector space of 2 power n dimension, like the dimension 2 power n for n qubits. Why? Because the like if you want to describe all the basis vectors for a system of n qubits, you would have like say you have two qubits, 0 and 1. What are all the possible basis vectors for that? You have 0 0 0 1 1 0 1 1, so all the binary combinations, so that would give you 2 power n. So that is the dimension of the vector space, because that is the total number of basis vectors required to span a Hilbert space. Now the important thing to note is that it's closed, as in if you have like an infinite sequence of vectors, they should converge. Like they should converge and not into the Hilbert space. The sum of that should not lie outside the Hilbert space, and that is something that's pretty important. It should be remembered. So qubits are basically can be considered as vectors inside the Hilbert space. Here, if you can see, it's like the states 0 and 1 are pretty like standard computational basis. So the state 0 is the column vector 1 0 and 1 is the column vector 0 1. So these are the basis vectors, you can say, for like a qubit in the Hilbert space. Now, I've been talking about qubits for so long. So what is a qubit? It's a fundamental unit of quantum information, just as a bit is for classical information, and it can exist in a state of superposition. That is, it can exist in a state of superposition. And there are multiple ways of representing a qubit depending on what aspect of a qubit you wish to focus on, and so on and so forth. It can be thought of as a vector in a Hilbert space, as a wave function. You can represent it through block spheres, which I think Archit will cover next week. So a qubit can be like mathematically represented as a vector psi with that, you can see here, and I can't exactly spell it out. But here the coefficients a and b represent the probabilities that you will measure either the state 0 or the state 1. And the state 0 and 1, as I mentioned in the previous slide, they're column vectors. So the probability that you'll measure the state 0 is a square, and the probability that you'll measure the state 1 is b square. And obviously when you add up a square and b square, you should get 1 because they're the probabilities. Similarly, you can have multiple states. This is for a single qubit. You could have, say, 1 by root 2 state 0 plus state 1, and the probability of measuring both 0 and 1 would be exactly half, stuff like that. So they represent the probabilities when they're squared of measuring that particular state. Now, like you can see the bracket notation here. What is the bracket notation? A ket, this is a ket, a ket can is basically a column vector, and it's a denotion, it basically denotes a vector. Now, a bra is the like vector dual to the ket, in the sense that it can be understood as a linear functional. What is a linear functional? A linear functional is basically something that takes a vector, like in two-dimensional vector, and maps it to a scalar. Like if, say, for example, you have 4i plus 3j or something. This is in a classical like 2D vector space I'm talking about. So 4i plus 3j, and you have some function that just gets you the x value, say the coefficient of I basically. So if you put that vector in this function, you should be able to get just the coefficient of I hat. So that basically maps the vector into a scalar value. So a ket can be thought of like that. A ket basically maps a bra basically maps a ket to a scalar value, complex scalar value, which this is basically denoted as the inner product, right? When we do an inner product, I'm sure most of you remember that, you get a scalar value. So when like you have a bracket like inner product, you get a scalar value. So a bra maps a ket to a complex number, to a scalar value. Now we'll come to some basic things we need to keep in mind before jumping into quantum computing. Hermitian operators and observables. Now, what are observables, right? Actually, I hadn't really heard about it before I started, quantum computing. What are observables? Observables are things that you can observe, physical quantities that can be observed, like, position, momentum, energy, spin, etc. So observables are physical quantities that can be measured in a quantum system. So it is the position or the momentum or the energy of that system. And they are represented by Hermitian operators. Why, what is a Hermitian operator first and foremost? A Hermitian operator is a self-adjoint, like as in this dagger, a dagger that you can see. What does this represent? It is the conjugate transpose, as in if you have, say, like, I'm sure you guys know what a conjugate is of a complex number, right? If you have a plus ib, the conjugate would be a minus ib. So a conjugate transpose would be you have a column vector of complex numbers and you get the conjugate of each of them and then you transpose it. So that is what a conjugate transpose is, and that is the Hermitian of a particular operator. So sorry, that is the self-adjoint. And a Hermitian is when the operator itself is equal to the conjugate transpose of itself. So that is what a Hermitian operator is. Now, why is it that we use Hermitian operators to, like, show observables? What's the necessity? Obviously, when we are measuring the position or momentum, these things cannot be imaginary. You need to have a real value for them. So the thing is that the eigenvalues of Hermitian operators are always real. That is a property of a Hermitian operator. So and the thing is that whenever you measure an observable, the values that you will get will be the eigenvalues of a Hermitian, of the Hermitian that you're using to represent that observable. So that is why we use Hermitian operators. Now, what is a Hamiltonian? It's quite it's a common phrase that comes up, common word that comes up. A Hamiltonian is a particular type of Hermitian operator that represents the total energy, the kinetic potential energy of a quantum system. And now, like, you might get a question, that we were talking about qubits, then we came to Hermitian operators and observables. What exactly is the correlation between that? When you measure a qubit, you are measuring a certain physical quantity of it. So you are measuring, the measurement that you're making is of an observable. So you get the measurement that you get out of measuring a qubit corresponds to some eigenvalue of that observable. Like, one very common observable is the Pauli spin matrix. You have sigma x, sigma y, sigma z. Again, that is something that can be expanded on next week. Like, so depending on which sigma x, sigma y, sigma z it is, the basis vectors or the eigenvalues will be either 0, 1, or plus minus states, etc. So they come up quite a bit. It's good to have like an idea of them. Now, I've been talking about measurement for quite a while, right? So what is a measurement? The game that we had like last sem, right? Everybody knows that when a quantum system is observed, then it collapses. Otherwise, it's in a state of superposition, right? So when you measure, you observe the quantum system. You're trying to see what the information held within that quantum system is, and when it's observed, it interacts with the environment and it collapses into its basis states, right? So you might, like, a qubit might be in, like, a0 plus b1 superposition, but whenever you measure it, you either get 0 or 1 state with the probabilities that accompany, with respect to the values of a and b. So at least I had this question when I was introduced to the idea, that why is it that, like, classically we have 0 and 1. Now with a quantum computer, we have 0 and 1 states with certain probabilities. So what exactly is the point of having a quantum computer or whatever this is? Because how is it any better than what we have classically? Isn't it just a bit of more headache, like you have to calculate probabilities and all? So the thing is, the way you design quantum algorithms and, the way, like, that is pretty tricky, because you need to make sure, because you can't measure the information held in the superposition. So you must do it in such a way that you get the right answer. So basically, the computation is done in a state of superposition. So you can access multiple states simultaneously, but you can, like, that is called parallelism actually, which I mentioned earlier. And then you use constructive interference, because I did say earlier that a qubit or qubits can be seen as wave functions. So you can use constructive interference and destructive interference to, like, you manipulate that in such a way that you amplify the results that you want and you cancel out the results that you don't want. And one of the examples of this can be seen in the grower's search algorithm. The algorithm, I mean, the state that you wish to search, you can amplify that amplitude and you can decrease the others. Like, for example, I mean, I won't go too much into it without going into what quantum gates are, but if you have a state, say 1 by root 2 0 plus 1, I mean 0 plus 1, and you apply a phase flip and you get 1 by root 2 0 minus 1. Now if you interfere them, the probability or the coefficient of 1 becomes 0, so there is no probability of measuring 1 at all. So that way you can, obviously it's a lot more trickier than that. You basically amplify or, sort of destructively interfere whatever you don't want, and you amplify the results that you want. You amplify the probability of measuring the results that you want, and once measured you get the output. Now, it is not that quantum computers are particularly efficient in everything. It's not that I'll use it for all the problems I want to solve in my life. It's that it's efficient as of now. What we know, the research is still going on, for certain types of problems, stuff like simulation problems, search problems like Grover search algorithm, optimization problems, stuff like that is much more efficiently solved on a quantum computer. So there are certain sets of problems that quantum computers, due to their nature of, superposition, entanglement, and interference, these things can be utilized to get a much more efficient, you know, solution for problems that classically are, not solvable in polynomial time. Now, what are, like, how are qubits implemented on hardware? Again, I'm not very familiar with this topic. It's, like, how do you actually make physical qubits? There are, multiple, ways with which you can actually implement a qubit. IBM uses superconducting qubits, and you can have trapped ion qubits, semiconductor qubits, topological qubits. I think that's something Microsoft is working on currently because they're quite, fault tolerant, photon based, stuff like that. So anybody who's interested in the hardware aspect of it can look into that. Now, like, I'll end the presentation on the note that, what is the stuff that is actually being researched and worked on currently? What are the avenues that quantum computing is actually used for? One aspect of it is, of course, the quantum hardware, like building and the nanotechnology behind it and all of that. Secondly, and quite, importantly, it's error correction, because one of the problems we face with, like, we've already been able to implement growers and shores algorithms, right? But the reason we cannot scale it to a very, very large extent is, of course, one, non-availability of so many qubits, but also that there is a lot of error when you run it on a real quantum computer because of noise. So even the smallest of noises actually, disturb a state. So, when you scale it to very large levels, the output that you get is pretty incorrect. So quantum error correction is something that is currently going on. Yeah, as I mentioned, even Peter Shor's working on that. You have quantum machine learning and topological quantum computing, which I believe the Microsoft is trying to come up with that. Because they're using Majorana fermions. I don't remember, but like, they're trying to make it very like noise, like, not disturbed by noise. So the error correction part is prevented. You have quantum communication and cryptography. Quantum communication using entanglement, and quantum cryptography, of course. And I think, yeah, I think RRI and ISRO are working on one of these. I don't remember, but it's also a pretty hot topic. Then we have simulations, many body problems, etc., etc. So these, I mean, of course, there are many other topics that I haven't covered. These are the things that are currently going on, and if anybody of you is interested, I mean, there are a lot of avenues to go into. It's still in the early stage, so, there's a lot of development going on. So anybody who's interested can look into that. And done with my presentation. Yeah. Does anybody have anything to say?
I don't have any questions. Does anyone have questions?
Not really, just thanks for the presentation. It was nice and simple.
Yeah, it was great. I mean, I had no idea about all of these things. It's kind of cool knowing all these things.
Yeah, Ashmita, really well done, by the way.
Thank you.
Yeah.
Nice. So we wrapped up before time. That's even more impressive. Okay. Who is okay? Next meeting about this would be the Saturday after the next, 2 Saturdays a month. Am I right?